Okay, so this morning, everybody who showed up this morning said they'd heard of Skyline, but maybe we high graded for the people who had heard of Skyline because why else would you be there? So is there anybody in the room who hasn't heard of Skyline? Okay, well that's great. Okay, but I'm going to give you an overview anyway. Sort of as Skyline grew, out of just being an SRM tool, we had to I had to come up with some definition of what it did, and when I would be asked to speak at quantitative proteomics workshops and things, I had wanted something to differentiate it from doing isobaric tagging and spectral counting, which are other quantitative methods that people use in the proteomics community. So I came up with this term, I think I came up with it, chromatography-based quantification, sort of encompassing all things that we're extracting chromatograms for, and then we're sort of always in mass spectrometry working in this three-dimensional space of intensity, which is ions per second, mass to charge ratio, and retention time. And now actually we have a fourth dimension, ion mobility, but we're not going to get into that here. But then, then in these chromatography-based methods, we extract chromatograms. We've been talking about this for a day and a half now, and then this is the way they get shown in Skyline, and we use the area under these curves as a proxy for peptide quantity. And so these are the four different methods that Skyline supports. I think about them in this 2x2 matrix. I think we've gone over most of these at this point, but there are true targeted methods where you tell the mass spectrometer what you're targeting, and then there are what I call survey methods, and both DIA and DDA are what I think of as survey methods. You set up the mass spectrometer in a specific way and let it sample the entire space, and then you come back and query the data afterwards. And one of the big differences being that in DDA you can only query the MS1 spectra for the quantities. There's no systematic sampling of the MS space that you can use in DDA data. But lots of tools do this where they just extract the MS1 space, and Skyline is one of them. Something unique to Skyline is right from the start it was designed to be multi-vendor. It was paid for by the National Institute of Health, NCI, National Cancer Institute, CP-TAC program that was at the time doing like a 10 lab study with 14 different instruments from Agilent, SciEx, Thermo, and Waters, and then later Shimadzu and Bruker came along and they were interested in. Now all of these vendors are funding Skyline. And working very closely with us. We have experts at all of these companies that are interacting with us to try to make sure that Skyline stays working on their instruments well. And so I guess the side benefit is that you can learn Skyline on some instrument. And DIA you can do DIA on Bruker instruments, in fact, and then you can go to another lab that uses a different instrumentation. You can still keep using Skyline. So in the first year of Skyline, this is a schematic that I drew to sort of express what we were trying to do, which was use discovery, use things coming out of discovery proteomics to do this targeted method refinement cycle to produce a high volume quantitative assay, potentially clinical assay. And now with DIA and actually DDA, we're moving, Skyline is moving up to actually help with discovery along with many, many other tools. There's quite a lot of tools up here. Most of our DDA, most of our discovery still, and even with DIA, if we're building libraries, we're getting a lot of information from DDA acquisition. And again, another area where Skyline is extremely broad is its support for these peptide search engines that we use on DDA data. And there's 20 different pipelines that Skyline supports, and anytime somebody creates a new pipeline, like one of the more recent ones was Morpheus out of the Kuhn lab, people just contact us and we integrate that. And so I haven't heard of a search pipeline in a while and that we don't support, and when we do hear about them, we can usually support them within a month or two. So let us know if you come up with So this targeted method refinement cycle I was talking about, probably, I think we mostly still think about it in sort of targeted acquisition modes, although, so I would say that there's less of it still happening in DIA, but I think it's still applicable to DIA, so worth thinking about, which is that you would build a method. So this might be targeting something, or you can use DIA to prime this targeted method refinement cycle now. Then run the method on the mass spectrometer, evaluate the results, and then you might refine your method. And in this refinement, you might be doing, one of these growing number of exercises, and you can apply this to DIA data to do more targeted DIA, which you're going to get more precise measurements. So you might be doing a pre-experiment to understand the abundance and measurability, and so that you're only measuring the highly abundant measurable peptides for a protein. You don't necessarily need to measure 20 peptides for a protein to quantify it. We look a lot at degradation. We do a specific experiment where we run a sample once and then run it 72 hours later and look at what peptides are degrading. And there are, there's a fair number of peptides that degrade, and if you pay no attention to that, then that's just if you do your experiments well, which means you did randomizing and blocking the way that Olga Vitek was describing, then that will be noise in your measurements. If you do them poorly, that can become a confounding variable, because if you didn't randomize and you've got degrading peptides, then that can cause certain things to look like they're upregulated or downregulated just because the peptides in the things you're measuring are degrading. We look at digestion kinetics, and then there's scheduling and optimization that can be done. So all that can be done with Skyline. It's supported by Skyline. Quick overview of the Skyline project. It's in its 10th year of development. In August, it will go into its 11th year. We're almost 10 years old since I started working on it. 7 developers now, 500,000 lines of code. It's all open source. You can read it. You can make modifications and send them back to us and talk to us about the code. There's 60,000 lines of code for testing, both our testing framework and all the tests that we write. We write a lot of tests, and most of the developers on the team feel that our test bed is one of our most valuable assets. There's over 10,000 registered users, so over 10,000 people could get an email when we blast, and they don't tell us to take them off our email list. So that's some achievement. And then 2,000 users are registered for Skyline Daily. So Skyline has 2 releases. Daily is sort of updated more like weekly or every few weeks. And it's our beta release. It's up to date, with the latest developments. If you register for Skyline Daily, you'll just hear about what we're adding. And somebody here spoke to me earlier today, was clearly on the Skyline Daily list because he said, whoa, we just heard you're supporting Bruker-Timstorff. And so you'll get those kind of up-to-the-minute updates if you're on Skyline Daily email list. And there's over 8,000 instances started each week, over 16,000 citations. And as I said, it's still funded by NIH, but also the 6 instrument vendors. This is a plot of usage over time. I originally thought that I'd be working on Skyline for maybe 2 years, and I wanted to be really sure that it was worth my time. So I just very quickly started tracking, are people actually using this? And I was pretty excited. This line is when we hit 1,000. I was like, wow, 1,000 startups in a week. That's amazing. And this is up to right now. You can see that the 4.1 release was very popular. And and then we come back after everybody downloads it. We sort of come back to reality. But this blue line on the top here, that's Skyline Daily, and you can see that when we have long release cycles, more people start using Skyline Daily because they want to get the newest releases. They want to get the newest features. And then you can also see that each one of these is a new release. We watch pretty closely how quickly the last release gets squashed by the new release. You can also see that the lighter color is 32-bit systems, and so we're running out of 32-bit systems. We'll probably discontinue Skyline 32-bit soon. And if you're doing DIA, don't use a 32-bit system. It'll just run out of memory and die. So this is that same graph flipped to just show what percentage of the people starting up Skyline are starting up the latest instance or Skyline Daily. And, so this is, I think, a testament to our testing, is that we always sort of get up around 95% before each release, and those release cycles are only about 6 months. So every 6 months, we're turning over and people are accepting our new releases. They're not going like, whoa, 3.5 was the last time Skyline had a good, stable release. So that's a sign of trust. It's also incredibly worldwide. You could go get a job anywhere. And I knew a guy from, I think he came originally from Europe, one of the first people using Skyline as part of the CBTAC consortium from Europe, Pavel, and he was in New York, and now he's down in Queensland, Australia. And so, and he's been using Skyline the whole time. So you not only are you not constrained by instrumentation, you're not constrained by locale. And it's been really exciting to see these areas where it's growing, increasing. We localized Skyline to Chinese and Japanese, and we've had a lot of uptake in that region as well. This is zooming into Europe, and you can see that we've had since very early on, we've had a close collaboration with the folks here in Zurich, and they've always generally topped the list for European European cities accessing the Skyline website. I guess pretty early on, we realized that this was not a viral product. We were in no danger of catching up with Facebook, and so I was super excited when Tina Ludwig in the back said, "Oh, we're going to teach a course," because we've been talking about teaching a course. We need to teach a course. We need to teach a course to teach people about targeted proteomics. And Tina said, "We're going to teach a course. Do you want to be part of it?" And I said, "Of course." And that was 2013. We started the first course here at ETH on SRM. You saw the whole history from Ben, and that's grown to all over the world. We're teaching about we've been teaching about 5 week-long courses and about 3 to 5 workshops at various places. 2018 kind of blew me away. There's a lot of people wanting new courses, a new one starting up, week-long one starting up at Duke in North Carolina, and we're doing one in Shanghai, which is pretty exciting, and then workshops too. And I'm actually sending out a group to Brazil that Tina's part of, and I'm not even going to go. One of my favorite quotes from a course in Brazil was somebody said, after the week-long course, that I realized I'm only using 20% of what Skyline can do, and my response was, "We only taught you a fraction of what is possible, so maybe you're still only using 5%. So there's a lot of documentation if you decide after this that you're interested in Skyline and you want to use it. There's actually 17 tutorials. I stopped showing thumbnails here at 12. 9 of them are translated to Chinese and Japanese, so tell your Chinese and Japanese speaking friends. And we've been doing webinars, because actually teaching courses like this and watching various people come up with new resources to teach Skyline, realized that we were frequently only teaching to, now here we're teaching to 50, but for a long time we were teaching to 30 to 25 people at a time. And so to get that information out more, there are a number of recorded webinars, and they're all what I call tutorial webinars, which is they're directed at teaching, directly teaching you how to use Skyline. You can download data sets from the pages, and then you can watch the tutorial. And so if you like the style of what we were doing here this morning, and what we call a Sky Jam, these will walk you through things. And some of them have companion written tutorials, and then there are some that don't. They're just like, well, we don't have time to write a tutorial, but here's some information you can get on a webinar. Skyline has sort of expanded beyond its own boundaries by including the work of others in external tools. And there's a little button here on the website where you installed Skyline from, where you can get to external tools. That's Skyline Daily if you're interested in getting that. I think, oh yeah, we're using a VM, but we're using Skyline Daily for this course because some of the features are newer than our last release. You can also get to this tool store in Skyline, and what the tool store does is it supplies a set of tools. I think they're around 15 now, and it comes with one default SRM Collider, which is by Hannes Roast of OpenSWATH. We put his tool up there by default, but all of these tools can be installed right onto the menu of Skyline, and you can then use them point and click. A lot of them provide UI, and most of them will export data out of Skyline and then analyze it. And so these are our 6 most popular tools. We're going to teaching MS Stats here. We teach it at most of our courses, and that's why maybe partly why it's been downloaded over 12,000 times now. But there are these other tools as well. I invite you to look more closely at those. Another way that Skyline has expanded beyond its bounds is this thing we call Panorama, originally developed by Vagisha Sharma here, and now actually co-developed with LabKey Software that developed this. It's a server with a database, and it allows you to publish fully annotated Skyline documents. You can now publish to something called Panorama Public. You can upload them to your own project, or you can then take something and publish it to Panorama Public, either just to get it out there and share it with people, or to use it as supplementary data for a paper. And it's now cited by the MCP guidelines released in 2017. If you're doing a true targeted experiment with PRM or SRM, it's suggested that you deposit your data up in Panorama processes with Skyline. There are 78 public data sets and 27 more in review. You can build something called chromatogram libraries, which allow you to take targeted data and use them again in targeted experiment. And then we're really super excited about this quality control or system suitability tracking that you can do with Panorama. I'll show you something about that in a second. That is all free and hosted on panoramaweb.org. Over 300 people have projects now. It's user-controlled security, so if you can have a project for just yourself or your lab, or something for a consortium, or you can have a completely public project where you can create your own identity, like these CPTAC links and this APRF CRG. They all have sort of public-facing projects that look like websites, and you can control how public you want to make it or how private. And then if you really need to make things private and you're a company, a number of big companies are using their own servers. So they don't use panoramaweb.org because we have to administer it, and they're not allowed to do that. It's got to be behind their firewall, so that they're installing servers and working with us with support contracts. But otherwise, it's developed free and open source under Apache 2.0, just like Skyline. This is a schematic showing Skyline in its targeted method and refinement cycle. It then uploads to Panorama. This is from the paper. Once a Skyline document is uploaded to Panorama, a lot of it can be viewed by people who have no idea what Skyline is. They can just navigate a website. And then people who do understand what Skyline is can download either chromatogram libraries as a resource or those uploaded documents. And then with the data that's up in the Panorama server, you can do various analyses. So this is AutoQC. This is a system for doing system suitability tracking over time, and this is just how one of the views looks, where we've got these gray boxes represent training areas where you train what you expect to see out of the system. And I guess this is a Levy-Jennings plot for retention time. So this is what we expect for retention time out of our peptides, and then we retrain it here, and now we expect our measurements to fall within 3 standard deviations of the variance in this range. And then you can see that we can also add annotations for what's happening to the instrument. And this is an incredibly powerful thing. Once people get using it, they really hate to give it up. And we have broken it a few times and heard very quickly from the people who were using it. So these are a couple of plots from Lindsay Pino in our lab, which are kind of fun. This is you can see just a 2-week period of time that she was tracking these peptides. This is a subset of the Pierce IRT, the PRC Is that what it's called? It's the Pierce Thermo Pierce PRTC kit. I just looked at it this morning, and they've dropped some peptides. And I would say that similarly, if I were going to try to use, say, the Biognosis IRT kit, I would drop some peptides because there are some that don't have stable peak areas. And so then you're going to have a lot of variance in here. So some of the peptides are better than others. And in this case, Lindsay has high graded the ones that she feels are quite stable. And this is her tracking of the peptides over time. You can see these big drops in 2 of her measurements in peak area. I think maybe she said this is when the sample vial ran dry or something. I forget exactly the reason. But then if you look at retention times are really quite stable. And even like you can see a couple peptides sort of drop out when the sample vial goes dry. But for the most part, you can actually measure the peptides at fairly stable retention times over the entire 2 weeks. And then this is one that I really liked, which was she's measuring mass error, and you can see it's up to about 7 or 8 here, and she recalibrates. And then, well, we get a little crazy again with some couple of peptides when the sample vial's gone. But basically it drifts back to almost 10 mass error. So you could track that and you get alerted to that when that's happening, and maybe recalibrate before you get quite as far out again. So one of the things that I decided is our reason for being with Skyline, and sort of one of my great interests is just allowing people to see the data. And definitely when I started with the program, one of the mass spectrometrists told me, boy, we've been doing this. We did a whole study. We got 10 labs together, did this thing, and everybody collected data, and we had no idea what kind of data we had until we sent it off to statisticians. And then like weeks later, they told us, which labs had done well and what was good data and what was bad. And I was like, I want you to be able to see that the moment it comes off the instrument. So I've always been, Skyline has always been about seeing your data. And after reading Daniel Kahneman, who's a psychologist who just basically talks about how prone we are to jumping to conclusions and getting things wrong, I decided that, well, what you see is what you believe. And if you don't see enough, you'll come up with just wrong conclusions. So, and this is my satellite view. You can see this is just an actual satellite picture, and you can learn things from it. Like there's a lot of center pivot irrigation going on, and there's certain areas that are browner. Maybe they're being left fallow, or maybe they just don't have enough water. I don't really know, but you can learn things from this. But you can't learn everything, obviously. This is our satellite view in proteomics, and a lot of people want to get to this and then, as quickly as possible and start coming up with biological conclusions. And I think you've already heard a lot of cautionary tales about maybe why you shouldn't jump to this so, too quickly. But yeah, I think you should be asking what's underneath these values, and Skyline's a great tool. Even if you use some other tool like OpenSWATH or whatever to come up with this satellite picture, you may still want to, like Ludovic clearly did, look at what's underneath. And often what's underneath are sources of error, and you can figure that out and maybe change what you're doing in your acquisition, or change things, or report a bug to Skyline and we'll fix it. This is one case where there's a clear error. This is not very smooth signal, and Skyline has mispicked the boundaries of the peak. So this is not the full peak. We would prefer that this boundary here, these 2 top boundaries with the arrowhead, those are the boundaries Skyline's picked, and we would prefer to see this one over so it came down in here. And so that's going to, if this is label-free quantification, that's going to quantify this a little bit too light. Here's another case where there was interference. This is all DDA data like we were looking at this morning. And so these are 3 isotopes. Again, Skyline's picked the boundary kind of wide. Maybe it could have picked it between this interference, would have been nice. But even so, this interference is going to be contributing signal to this no matter what. So interference in general is just a source of error, and getting some sense of how much interference you have is important, and you can learn that from Skyline. Here's one where it was actually a bug, but all software has bugs, and we fixed this one, but somebody was able to point it out to us because Skyline's so visible. Here's an ID right in the middle of this peak. That really is the peak we want picked, but instead this other peak was picked. And so if you have a tool that just spits out a bunch of numbers and then you never go back and inspect them, you're prone to all these sources of error. Just to orient you, this is Skyline's, how Skyline supports labeled internal standards. You can see a heavy and light pair. This is a modification defined in Skyline. And then they show up as blue for heavy and red for light. So, and then this is some of the nicest chromatography data I've seen coming from the CPTAC program in their study 7. And I just say that chromatography-based quantification depends on chromatography. And here is super nice chromatography. It's very, very stable retention time. And then, nice smooth half-minute peaks. The isotope labeled standard is very, straight across here. And this is a response curve experiment, a calibration curve. And you can, even without any normalization, you can see very stair-step peak areas for each concentration. This is less nice chromatography, and if this is what you saw when you looked at your data, then you should not necessarily expect it to have as nice a satellite image as this, right? So you need to know what the quality of the data is underneath, and you can monitor that also with system suitability as well. So we've talked about this. I think we've actually even shown pictures like this. This is actually from a low resolution ion trap where the blue is the precursor and the colored are the fragment ions, and this is just showing that MS1 by the time we get down to 20 femtomole is almost swamped by noise. This is not a high selectivity instrument, but or not a high resolution instrument, so it may not be quite this bad, but in general, this is what we see, that the MS1 is going to end up being less sensitive because it's less selective. So sensitivity is based on signal to noise, and we generally just have more noise in the MS1. And it doesn't always even look this good. Sometimes it looks like this. These are the 3 precursor isotopes showing up, and the fragment ions should barely show up at this scale. They look quite nice like this if you zoom in. But after seeing this, I ran into Mike's office and I said, we're going to get more precise signal out of the MS1 because there's so much more ions flowing to the detector. And that was, like Ludovic, that was one thing that I said that I think I was totally wrong on. So decreasing noise increases signal to noise, and that's part of why people started doing SRM. And this is a schematic that comes from what's the era of this paper, or Mike?
This is the old MacLean textbook in mass spectrometry.
And when was that? I keep saying.
1980s or something.
Yeah, 1980s. So this is from the 1980s. It's a basic principle of mass spectrometry that if you can decrease noise, or any analytical chemistry, if you can decrease noise faster than you decrease signal, then your signal to noise goes up, and that's going to increase your sensitivity. So don't let people tell you that just the sensitivity is just dependent on the number of ions. It's also dependent on the selectivity and the level to which you can measure the right ions. So selectivity also, but when you're thinking about selectivity, you got to be thinking about sample complexity. So you may not need, you may not need a lot of selectivity. So if you're analyzing purified sample, I was telling somebody at Johnson & Johnson, this is why you would use SRM, and he said, look, I'm measuring biological drugs that are purified. MS1 is perfect for me, and I was like, oh, you're right, because you don't need the extra selectivity. So, and this is again what we've seen before from the original SWATH paper and I say that I'm unsure that this is really the lower limit of detection for this label-free method because there's some loss of linearity. So maybe it's like this, but yes, SRM, SWATH, MS1, we've seen lots and lots of data since this paper that make us pretty confident that this is our ordering in a complex sample because of the selectivity. This is the Skyline team, many of whom are back in Seattle working on the next release and ready to support you if you ask questions. And yeah, they did a lot of the work and continue to. And so I'm open for questions. Yeah, I'm done. That's it.
Okay.